All right, so in this video, we're going to be continuing with the MATH271 final review on BVPs 1 through 7. So the second problem here is derived from the course pack, page 112, and it's basically the derivation for BVP 7. However, I just used a length of pi instead of just an arbitrary L, just so that we can get some more practice solving this type of BVP. So first, the question is asking us to solve this form here. So this is BVP in terms of three parameters, x, y, and z, where each parameters vary from 0 to pi. And then we are subjected to different boundary conditions here. And so basically the question is just asking us to find the phi value that satisfies this equation. So here, for the solution, if we want to interpret it physically, it's that phi of x, y, and z is the potential or the steady state temperature distribution in a parallelepiped with x equals 0, x equal pi, y equals 0, y equal pi, and z equals pi faces maintained at 0. So we can see all the green faces of this cube are maintained at 0, while the z equals 0 face is maintained at f of xy. So that's some arbitrary function. It could be defined as anything. We just left it as arbitrary for this problem. But yeah, so that would be the physical interpretation. And so steps to solve, this is really just going over the steps on how to solve the BVP 7, but just to get some practice. First, we want to let phi of x, y, z equal a function of these three variables. So this is really similar to how we solve the other BVPs that we found. We use separation of variables, plug it into the PDE, and then solve each eigenvalue equation respectively. So, but just now we're dealing with three variables instead of two. All right, so we're plugging that into the PDE. We will get the following. This is the first term plus the second term. And then our last term equals to 0. So now we just multiply both sides by our 1 over, and this time it's x, y, z, because we have, again, three variables, and we will get this. And I'm just bringing the y and the z term to the right-hand side because I want to get my eigenvalue equation in terms of x. So to do that, I set it to a constant, and we're going to call that constant lambda. So next, what do? We solve this eigenvalue equation. And remember, based on our boundary conditions, we can find that x of 0 equals 0 and then x of pi. So that's just manipulating these boundary conditions that we were given. Specifically this first row here. So this can simplify down to x of 0, 0, and then x of pi is 0. So these are obviously Dirichlet boundary conditions, and we know that only negative values of lambda will yield non-trivial solutions. So we know the answer to this specific eigenvalue equation. But remember, in this case, that our L is actually equal to pi. So I just did that just to, simplify the solution, but you could have any arbitrary L. and then where your lambda is the negative case. All right, now the next step is to solve the remainder. But here, because we still have kind of a function of two different things, we're going to want to isolate for y first. Just you could isolate for z first, but I chose just to isolate for y first. So we're going to write y on our left-hand side and then bring the z term over to the right. So all right. Oh, sorry, this should be a minus. Yeah, because I'll move the y over and then you have to move the lambda over. So that's why you get those two minuses. All right. And we're going to call this another constant and we'll just let that be mu. So just pick a variable. I chose mu. And so we're now going to solve this eigenvalue equation. And using the boundary conditions, again, these are Dirichlet, but in other conditions, you could have Neumann here. So this just all happens to be Dirichlet for simplicity, but just know that you can also encounter different types of boundary conditions. And so we know that this eigenvalue equation for non-trivial solutions, mu must be negative, and it'll give us this expression. And now we are using k just to differentiate it from the previous one. All right. Now that we have this, we can finally move on to our z. So we want to solve just now that's negative k squared. So bring it to the other side. So I plugged in lambda and mu. And to solve this, we're going to let this term here, we're going to let it equal another constant. All right, so now this right-hand side is equal to this constant. Oops. And here we can make this constant and just call it in terms of both n and k. You don't need to define a new iteration or iterative variable. We can just say that this variable iterates with both n and k. And from there, now we're going to bring the z to the other side. So if I just write it out like this, and then bring that z over. And we know this is a second order, order ODE with constant coefficients. And the solution to that will be, we'll use a variable c and D. And here we decided to use the hyperbolic solution to this ODE because we were given Dirichlet boundary conditions for the Z variable. But if we were given Neumann boundary conditions for the Z variable, then we would want to use the exponential solution. So from here, we can apply boundary condition in terms of Z. So here, this one will be the Z is equal Z of 0, 0, and then Z of pi is a function of f of x, y. So we do Z of 0, 0. Then the Z function just boils down to the D, the sine term. Right, because then that CNK term goes to 0 if we plug in Z equals 0 and set it equal to 0, right? So we're just left with this hyperbolic sine term, and we note that Z varies with both N and K iterative variables. So now, moving on to step 5, we're going to rewrite the PDE and let our AN, BK, and DNK equal a new variable, and we're going to call that ENK. So now, right? So here, when we use the principle of superposition, we comment on the fact that we want, so because our operator we're using that operator and it's equal to 0, that means we want the null space of this linear operator. Oops. So use the principle of superposition. And it's important to note this down on a test or an exam situation. It just really shows that you know what you're doing and everything you're doing is kind of like purposeful, and you understand really the theory behind why we're doing this. So it's good to note down. So now and here we're letting n and k vary to infinity because we're assuming that it's piecewise smooth. So you can note that down as well. But basically plugging everything in. This will be what our temperature distribution is looking like. And then the last step to do is to solve for our constant there. So to solve for that E of NK. And what we want to do, we're going to apply our last boundary condition. So we were given so if you plug that in, oops, not equals. We have this, so we just replaced our z with pi. And then what we want to do, we're going to take the inner product of both sides. And we know that it's the same as multiplying both sides by these terms and integrating. Right? So again, this is just something that is good to note, shows that you understand the theory behind it. You don't need to write this down, but it just shows your understanding. Right, so we will have as follows. And that is going to be equal to, I'm going to write it on the second line. E and K, parabolic sine, and then integral. And then our other integral in terms of y. Right? Okay. So then applying the Dirac delta, so we know this is also 1/2. Then we can rewrite this as so remember this is L over 2. So what we want to do here, because our L is pi, that becomes a pi squared. So I could have written that out more clearly. Let me just, right? Okay. So now that is going to be equal to our other side. And so in this case, because we don't know our function of x, the solution can't be simplified any further. So our E and K is just going to be equal to, if we bring everything to the other side, times the double integral and so we can't simplify this out any further. So if we just plug that back in to our phi function, we can get the final answer. So usually when I write down the final answer, you can just copy it down down there, or we can just say that ENK above and we have to define this again, and that was equal to n squared plus k squared. All right, so that would be the final answer to this type of problem. And yeah, thank you.